In this lecture, we are going to study dry friction or Coulomb damp systems. See, till now, we have been studying systems which are totally undamped. Undamped systems have an assumption that go with them, that although in real world there is a lot of damping that goes without saying with all sorts of oscillations and vibrations. But for simplification, we had assumed till now, or rather before the topic of damping comes up in your curriculum, that systems are vibrating or oscillating without any damping. And since you're assuming that damping is absent, so supposedly the system will keep on oscillating or vibrating forever till the end of time. But that idealization was more inclined towards developing a mathematical model. So once the mathematical models have been developed and the backbone is ready, then we can introduce the concept of damping, and that too in a mathematical sense. So to start with, let us recall that if you start considering damping in your system, then damping can come from many sources. And in your curriculum, we have divided or rather classified damping into the following categories. The damping could be of viscous type. So viscous type of damping comes in your system when there is some lubrication or lubricant between two surfaces. And when one of the surfaces or both the surfaces are moving relative to one another with a significant thickness of some lubricant separating the two relatively moving layers of solids. For example, let me say that the bottom, there are two plates as you can see in this rough figure that I've drawn here. Two plates of metal have been separated by a layer of lubricant in between them. The bottom plate is fixed and the top layer is moving to and fro. So in such a condition, viscous damping will come into play. If the damping or the resisting force is not coming from the presence of some viscous fluid, then it must be due to friction. So this is more commonly known as dry friction or Coulomb damping. Coulomb is the name of the scientist uh, associated with the development of the concept here. So dry friction means there is no lubricant between the rubbing or oscillating or vibrating surfaces which are in contact with each other. And due to dry friction, the resistance comes into play. It could be, if not of viscous or dry friction type, then the damping could be hysteresis. So hysteresis type of damping could be there. We will discuss about hysteresis damping in another lecture, so I'm not going to elaborate much on that. Or it could be interfacial damping. Interfacial means the type of resistance which is encountered at the interface of joints which are held under pressure. Anyway, our focus in this particular lecture is on dry friction or Coulomb damping. So I've prepared a set of notes for you here, and it's around, let me see, 4 pages, 4 pages or something like that. So Before we start with the mathematical treatment of dry friction or Coulomb damping, let us take a comparison of different types of damping. And to be more on point, this is basically a comparison between viscous type of damping and dry friction damping. So you see this graph speaks a lot about the difference between these two types of damping. This graph is basically drawn between the coefficient of friction between two mating surfaces, which could be rubbing over each other while oscillating or vibrating. And on the x-axis, we have taken velocity. So basically, this graph is representing how or how much the resistance is going to be affected by the velocity or the relative velocity with which two mating surfaces are rubbing or contacting over each other while oscillating or vibrating. Now you see, if you have a smooth surface and there is no lubrication, then you will have dry friction damping. And in that case, as you can see, no matter how much you increase the velocity. See, as I'm traveling towards the right hand side, I'm basically increasing the velocity. So this graph clearly says that in the case of dry friction damping between smooth surfaces, the velocity with which the relative motion is taking place does not matter at all. So the coefficient of friction is independent of velocity, more or less independent. Now, a small difference can be observed if you have a rough surface. See, a rough surface, when microscopically enlarged, you will see that there are a lot of unequal ups and downs on the surface like this. There are a lot of hills and valleys, and the depth and height of each hill and valley is totally random. So, if this is the bottom surface, then on the top surface also there will be such hills and valleys like this. Now, basically, when there is a rough surface, there is a very good possibility that the hills and valleys at many points might interact with each other in such a way that the valleys of some locations are going into the uh, valleys of another surface, the other surface. So in such case, you see this is an interlocking, this is an interlocking of surface peaks and valleys occurs. In such a case, what you have to do is, or rather in such a case, what you need to understand is that when you try to move surfaces with such heavy interlocking relative to each other, the resistance to motion will be very large initially. But as soon as the surfaces start moving with a certain velocity, then with the increase of velocity, these hills and valleys won't get time to come down and settle over each other. So this explains why in the case of dry friction damping with rough surfaces, the initial resistance or the coefficient is high, but with increase in velocity, you will see that there is a dip in the resistance, and then at higher velocities, even a rough surface behaves like that of a smooth surface. So in smooth surfaces, there was you actually saw no resistance or no correlation between velocity and the coefficient of friction. In rough surfaces, initially when they are at rest, the surfaces will show a very high reluctance in separating from each other because of the interlocking of hills and valleys. But once a certain velocity has been achieved between the two surfaces, then you will see that more or less both rough surface and smooth surfaces behave exactly the same. That means they almost become independent of velocity. Now look at the graph that is shown for viscous damping. It goes at an angle, and whenever there is an angle made by a straight line, you can see or you can observe that a slope will come, and this slope directly tells you from visual inspection that as you keep on increasing the velocity, your coefficient of friction is also going to increase. And this we have already understood because the force of damping in the case of viscous damped systems is directly proportional to velocity. And that is how we get the damping force equal to C into V, where C is the coefficient of viscous damping or damping viscous coefficient, or sometimes also called as the damping constant. Anyway, so the takeaway from this particular graph is that the frictional force of damping, or the damping force, which basically comes from friction in this case, is a constant. In the case of viscous damping, it is not constant. The damping force in the case of viscous damping is proportional to velocity. The damping force in the case of Coulomb damping is a constant, and it more or less does not depend on the velocity. Now, this we have understood. The damping force is constant. It will always be opposite to motion. Now, since we are talking about friction, everybody knows that friction always acts opposite to motion and independent of velocity. Yes. And frictional force, as everybody knows, is given by mu into R. So, if you want to find out what will be the frictional force for an object weighing mass m if it is pulled in a certain direction with a velocity v. So what will be the constant force of friction that will be acting continuously in the backward direction opposite to that of the velocity? So first you see that mg will be acting downwards, and the normal reaction in the upward direction will always balance this mg. So R in such a case becomes equal to mg, and the force of friction F as given by the universal formula of mu into R, where mu being the kinetic coefficient of friction. More appropriately, it is represented by mu suffix k, because there is another mu which is called as the static coefficient of friction. And these two are certainly different from each other. Mu suffix k and mu suffix s are different. But anyway, since we are talking about moving objects here, so we will be more or less dealing with mu k. Okay, so force of friction will be equal to mu into R. So in problems of frictional damping, the value of mu will be given to you. So mu multiplied by R means mu into mg. So mu mg will be the constant force that will be applied in the backward direction for masses moving over surfaces that are not lubricated, or for relative motion of surfaces which are having frictional damping or Coulomb damping. Anyway, now what is our objective in this particular study when we are studying about frictional damping? Like we had already discussed at the onset when we started studying vibration engineering as a subject, more or less the aim is always to find the value of omega suffix n, or natural frequency. You want to find out the natural frequency, and you want to find out how the behavior of the system would be, what would be visible mathematically and physically. So if there is no damping, you know that the displacement time curve of any oscillating body executing simple harmonic motion would be a sinusoidal curve. If there is damping, what happens is this displacement time curve will lose amplitude. So you see that once you start with a certain amplitude, As time passes by, this amplitude decays or reduces, and eventually with time it will go to zero. So you see, the amplitude you started with A, and after every cycle, this amplitude is getting reduced. So this is what happens in the case of damping. Now we want to observe all these things. We want to find out what will be the value of the natural frequency when there is damping. How will the amplitudes decrease? Because amplitude decrease is bound to happen. This will definitely happen. But how is it going to behave? Because in viscous damping, we saw that if you connect the peaks of all these reducing amplitudes, you get an exponential decay curve. This is an exponential curve. So if we have frictional damping, will we once again get an exponential curve, or would it be some different type of curve? One thing is for sure, the oscillations will reduce in amplitude, but in which fashion are they going to reduce? So these are the curiosities that we have to fulfill while studying this topic. So how will the amplitudes reduce, and what will be the frequency of oscillation? This is what we want to know. Okay, so let us directly study from the notes. That would be more convenient and it will save some time also. So this is derivation of natural frequency omega n of oscillations. First, we are going to derive the natural frequency. So consider this figure, figure 2. This is figure 2. I forgot to mention the figure number. I always advise students on putting appropriate figure numbers, but here I guess I myself have forgotten. So please pardon me. Figure number 2. The instantaneous position of a spring mass system vibrating with Coulomb damping is shown here. So you see there is a horizontal spring. It is attached to a wall here. And this dotted line, this vertical dotted line, this shows the mean position. That means the mass and the spring, when they were not stretched, when they were totally in a relaxed position, they were at this location. And obviously the ground is extending in both directions. Now what happened was, to start the oscillations from this mean position, you initially must have pulled the mass to some extreme position, let us say up to this point, and then you must have released it. So now what is going to happen is, from this position the mass will go here, then from this position the mass will come here, then from this position the mass will go here. Now you see what I'm doing? I am reducing the distance up to which the mass is going to go every time from the mean position. So if you see, initially this much ground was covered, and in the return path, let us say this is the mean line. In the return path, the object will not reach up to the point in which it had reached earlier. It will reach only up to here. And then once again, when it goes back, it will come up only up to here. And in the return path, it will come up to here. So you see, amplitude is being lost every time it travels to and fro from the mean position. Now, if you remember correctly, we had a certain way of deriving the natural frequency. What we do is, we draw the free body diagram, we draw all the forces acting on the mass by considering any random position during its motion, and looking at the forces acting at that random instant, we have three ways of deriving the differential equation of motion. You can apply Newton's second law, you can apply D'Alembert's principle, or you can apply the energy method. So that is what we are going to do. We will apply one of the methods in this by taking a random position. We will come up with a differential equation. We will solve the differential equation and then look at the structure of the differential equation. And from the structure of the differential equation or the solution, you can guess the value of omega n. This has been already taught to you in classes how to do this. So let us see whether we can do this in this case also, or rather how you have to remember this derivation. So this was the instantaneous position of the mass that was considered, and how is the mass moving right now? Is it moving rightward or leftward, or what is it? In the instance considered here, the mass is to the right side of mean position. Obviously, the mean position is here, and right now when you captured this position, the mass happened to be on the right hand side of the mean position, and it is currently moving leftwards. So see, while oscillating, if it is randomly oscillating about the mean position like this, the mass could be either moving towards the right or it could be moving towards the left. So you have to specify in this case, because this is important. The direction of motion is important, because if it is moving towards the right, then the force of friction will be towards the left, and if it is moving towards the left, then the force of friction will be towards the right. So in the case of frictional damping, it is important to mention the direction of motion also. So in this current situation, the mass is moving leftward. And since the moment when you captured the image of the mass, the moving mass, it happened to be on the right hand side of the mean, and mean position being considered as the origin point, you are measuring the instantaneous displacement of the mass by measuring, or by rather by taking the measurement from origin to the right hand side. So x is measured towards the right. So as soon as you see that the displacement has been taken towards the right hand side, you declared the right hand side as the positive side and the left hand side as the negative side. Now this is very important to declare a sign convention, because once the sign conventions are in place, now for every vector that you see or that you encounter after this point onwards, you will have to put a proper sign on it. Because in the free body diagram, you will be looking at forces which are helter skelter. That means some forces might be rightwards, some forces might be leftwards. So some sign convention has to be in place. So this is how we put the sign convention in place. You capture the instantaneous position, and in that position you see whether the displacement is being measured towards the right or it is being measured towards the left. So whichever direction the instantaneous displacement is being measured, by default we take that direction as the positive direction. Okay, so in our case, the right side is the positive direction. Now as you see, the free body diagram is drawn over here. FBD is free body diagram. So obviously at this position, the spring is stretched from the mean position by a distance x, and the spring force is given by k into x. So the spring is obviously trying to pull the mass back to the mean position, and it is towards the left hand side. And since the mass is in motion towards the left hand side, so obviously the friction must be acting opposite to motion, and therefore it would be in the right hand direction. F is the force of friction. And apart from this, obviously you can claim that there are two other forces which I have not drawn. I have not drawn them because you obviously have mg force acting downwards, and the ground on which the mass is resting will give an upward normal reaction r. But at every instance, while the mass is moving by sliding over the surface, the ground, this r and mg are always equal to each other, and hence they will cancel each other out. So it does not make much sense to draw them in the free body diagram. You could choose to draw them also. You could claim that a free body diagram should show all the forces. So you can draw these forces, but eventually they will cancel out. So let us say, for the sake of convenience, that right now we have only two contenders as forces acting on mass m. F is acting downwards, and or the spring force is acting leftwards. Now we apply Newton's second law of motion, which, as you already know, how do we apply that? We put mass into acceleration is equal to summation of all the forces acting on the mass. Now you see there are only two forces. One is F, one is Kx. Now you put the proper sign on these forces and add them up. So I say that F is towards the right hand side, so F is positive. and I have to add the other force also. But since it is towards the left hand side, the sign of kx is negative. So this is how I express the summation of forces. There are two forces. I added the forces. One of them happened to be negative. Therefore, what I get as the differential equation of motion by applying Newton's second law is m into x double dot. X double dot, as everybody knows, is d2x upon dt square. It is the second derivative of x with respect to time. To save space and to save time, we generally depict d2x upon dt square by putting two dots on top of the variable. So obviously, if instead of the second derivative, if you have the first derivative, you have to put only one dot over x. So this is once again to remind you, those people who do not know this type of convention, just to make them remember this. Okay. So now what I am doing is I am rearranging this equation. I divided the entire equation by m. After dividing it, I get an equation like this. This is equation number one. Now, generally, at this point of time, we will take a detour into the mathematics of stuff by saying that this is a type of equation whose general equation goes like this, and then we will go on modifying the general equation and all. But at this juncture, let me just tell you that it is okay for you guys to express the general solution of this differential equation directly like this. So you can remember it. We are not going into the details of the differential equation because our aim is to quickly arrive at omega n, and how we can arrive at this sort of structure has already been explained to you when you studied viscous damped systems. So the details of how to deal with differential equations has already been explained in detail over there. So refer to that lecture if you want to know how directly we made a jump from this to this. You got a differential equation from Newton's law, and then suddenly somebody is saying the general solution to this is this. Where did this cos come from? Where did this sine come from? The details of this are already explained in viscous damping. But anyway, you can directly claim that the solution to this differential equation can be generally given by this expression. Why are we calling it as a general solution and not the simple solution? Because this solution has two unknown constants, C1 and C2. And these two unknown constants have to be found by applying boundary or initial conditions. Now, once again, I will not be dwelling on this topic because the application of boundary conditions and initial conditions have been taught to you in class while you were doing your viscous damping. So anyway, the boundary conditions that you're going to use is that let at the beginning of time at t is equal to 0, you initially pulled the mass by a distance of x naught. So x is equal to x naught, the initial amplitude at t is equal to 0. This is the first boundary condition. And the secondary boundary condition is that you are saying that you happened to stretch this mass. Let me draw it and explain how the boundary condition. This was the mean position. Let us say this is the original mean position where the mass was resting without applying any stretch or compression on the spring. Now from this point, you stretched the mass initially by a distance of x naught. So this is what you are saying is the first initial condition, that the initial amplitude at which you are going to release the mass at t equal to 0 was x naught. And secondly, as the second initial condition, you are saying that at my time t equal to 0, I was holding the mass here and I had not yet released it. So what is the initial velocity of the mass? It is 0. So that is what you're claiming it. I was holding the mass before releasing it. So at t is equal to 0, the velocity is equal to 0. This is the second initial condition. So apply these initial conditions as you know how to apply it. And if your calculations are correct, I myself not included the details of the solution here. You apply 1 and 2, and you should be able to get the values of these two constants. See, why do we apply initial conditions to any solution of a differential equation? Because a general solution to any differential equation will always contain unknown constants, and those unknown constants are always calculated by applying initial conditions. So if there was only one unknown constant, I would have needed only one initial condition. But since I had two unknown constants, I had to make use of at least two initial conditions. So making use of these two initial conditions, you should arrive at the value of C1 as x naught minus f upon k, and C2 should be equal to 0. Now, since you know the values of C1 and C2 after application of initial conditions, you substitute these values into the general solution here. And when you put it over here, C2 is 0, so this entire term becomes 0. So your final solution should be x is equal to this. So equation number 2 is giving you the complete solution of your differential equation. And now let us see how the solution that is in front of our eyes is going to help us in finding what the natural frequency is going to be, because this was the claim with which we started this whole topic. We claimed that we are going to derive the natural frequency by developing the differential equation, right? So by looking at this solution, let us look at this solution carefully. X is equal to, this whole stuff is a constant. Okay, so let me put it like this: x is equal to some known constant. Now we know this constant. F is a constant, force of friction. K is a spring constant, it is also constant. And you pulled the mass by a distance of x naught, so you already know that as a constant. So all these terms are constant. So let us say we write it as capital X, which is equal to this whole stuff. Okay, so some constant which will be treated as the amplitude multiplied by cosine. Now see, a cos function is coming up of, generally whenever we have a cos function or a sine function, the thing getting multiplied by time would most probably be the natural frequency. And then you see, this in itself constitutes a simple harmonic motion. This is the equation of a simple harmonic motion. The only thing is that a constant of f by k is getting added to the simple harmonic motion. So this is a harmless addition of a constant. So this does not prevent the motion from being simple harmonic. So what we eventually understand from this is that the frequency or the omega n must be the set of parameters sitting here getting multiplied with the time. So by comparison with the standard differential equation, we claim that omega n is under root k by m. Now, this is something very interesting here, because we were interested to know how the presence of damping is going to affect the natural frequency. See, if this omega n equal to under root k by m is a very, very standard expression. So if somebody uh, directly starts a discussion with you by opening the statement with omega n equal to under root k by m, and if that person tells you draw the system that will show this frequency, so you will immediately say, oh yes, why not, I know that. I will suspend a spring from air, I will put a mass here, the spring has a spring constant k, and if this mass and spring are allowed to oscillate up and down, yes, then my omega n will be under root k by m. And then the person asks you again, is there any damping in the system? You say, no, 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 no damping in the system. So omega n is equal to under root k by m is the frequency of a simple spring mass system when it is devoid of any sort of damping. But then you did a lot of mathematics here. You put up the damping case also. You brought friction into this. You developed the differential equation. You solved the differential equation, compared it with SHM and Viola. What you are looking at is the same thing sitting over here as if there were no damping. So we conclude that in case of Coulomb damping, the angular frequency is omega n of the system remains unchanged. That means if the damping is of Coulomb type, then the frequency of the system will be exactly the same as that of an undamped system. सिस्टम ऐसा बिहेव करेगा जैसे कि, यानी फ्रीक्वेंसी के मामले में तो कम से कम सिस्टम ऐसा बिहेव करेगा जैसे कि डैम्पिंग थी ही नहीं. So the frequency of the system remains the same. I will quickly elaborate a little bit more what the meaning of this is. If there is no damping, then the displacement time curve goes like this. Sinusoidal, of course. Now, what is this omega n? This omega n is basically, see, since you have time on the horizontal axis, the horizontal distance between any two consecutive crests in the sinusoidal curve should be the time period, right? And what is time period in terms of omega n? It is simply 2 pi upon omega n. Now, if you have a spring mass system without damping, then all that we are saying is that in the time period of this sinusoidal oscillation, this omega n that is sitting down here will be equal to under root of k by n. Now, what happens if instead of a hanging spring mass system with no damping, you have a system with frictional damping like this? Now, the mass is rubbing over the surface, the spring is the same, the mass is the same. In this case, the displacement time graph will definitely be, being a damped case, it will decrease gradually. So the amplitudes are decreasing. But once again, you ask this question, what will be the distance between the two consecutive crests in this decreasing amplitude scenario? You will say that this is once again being the time axis, this is the time period, and you were expecting some omega d here. You were expecting that due to damping, the natural frequency would be omega d and not equal to omega n. So you were going to claim that this time period will be given by 2 pi by omega d. But this is what we found out here, that the natural frequency with damping, this is basically omega d here. Okay. The natural frequency with damping, which we call as omega suffix d, was found as under root of k by n, and which eventually happened to be equal to under root of k by m, which is the natural frequency of the system without damping, which we simply write as omega n. Okay, this is what we found. So we found that the omega d in case of frictional damping was omega n itself. So there is no change in the time period. So the time period of oscillations without damping and the time period of oscillations with Coulomb damping will be the same. It will not change. But please remember, had it been a case of viscous damping, then again you will see oscillations which are decreasing in amplitude. But now if you measure the time period, you get omega d, which is not equal to omega n. Actually, from the derivations, we find that omega d in the case of viscous damping is equal to omega n times under root 1 minus zeta square, where zeta is the damping factor. The details of this are already explained in the viscous damping lecture. So all you need to remember here is that for viscous damping, after the damping occurs, the time period changes. But for frictional damping, the damping will reduce the amplitudes, but the time period remains the same as if there were no damping. Okay, now let us move on. Now we are going to study how the amplitudes are reducing. Are they reducing exponentially like they did in the case of viscous damping, or are they reducing in some other fashion? So let us see how the rate of decay of oscillations in Coulomb damping takes place. Now for this, consider the figures shown here. Consider half the cycle of oscillation as shown in the three figures below. First figure shows that there is a long horizontal surface, the mass is resting here, and this is the equilibrium position. Equilibrium position means the spring is neither stretched nor compressed. Everything is relaxed. Now in the second figure you see, you physically extended the mass, or you brought this mass to the right hand side and extended it by x suffix a, because the position here is named as a, extended up to a, and now you release it from this position. What will happen? Immediately the mass will start traveling towards the left hand side. It will try to go back to the mean position. But since by reaching the mean position, by the time it reaches the mean position, the mass would have acquired a certain amount of velocity. And although there is a force of friction which is acting in the backward direction, in most cases, the inertia of the mass would be much higher for the friction to stop it at the mean position. So what will happen is, at the mean position, the mass will not be able to stop. वो अपनी खुद की इनर्शिया के कारण रुक नहीं पाएगा, और वो ऑफ शूट हो जाएगा और लेफ्ट साइड की तरफ जाकर के किसी एक बी पॉइंट पे आकर के रुकने को मजबूर होगा. It wanted to stop at mean, but it could not stop at mean due to inertia. It will go to the B point and then only stop. Now at the B point, as you can see, the B point is towards the left side of the mean position, this mean position. And all points toward the left side of the mean position indicate that the spring now would be compressed. तो अब जो स्प्रिंग फोर्स है वो इसको इधर को धक्का देगी. तो ये यहाँ पर रेस्ट में आ गया था, और कितनी दूरी पे आया था? We are assuming that a distance of xb towards the left was achieved by the mass for it to come to rest. And obviously you know that starting from A position यहाँ पर थी देखिए, और B position यहाँ पर है. A position से B position तक जाते दौरान मास घिसता हुआ गया है. It was rubbing with the surface, so it is continuously losing energy. So it is 100% logical to assume that xb, let me take the ink out of this paper, xb is definitely lesser than xa. अगर यहाँ पर फ्रिक्शन नहीं होता तो जितनी दूरी से m को राइट साइड से छोड़ा गया, उतनी ही दूरी पे ये लेफ्ट साइड पे अचीव करके रुकता. लेकिन फ्रिक्शन के कारण ये हो नहीं पाएगा. सो xb will always be less than xa. So b is a point when it comes to rest at b in return path, and that happens to be in the left side of the mean position. Now what are we trying to achieve by doing this? A position से खींचा, छोड़ा, b position पे जाके रुका. Essentially what we are saying is the travel of the mass from point A to point B on the left side is half a cycle of oscillation or half an oscillation. क्योंकि एक oscillation complete करना किसको कहते हैं? मीन के किसी भी एक साइड से छोड़ो, वो उसको क्रॉस करेगा, फिर वापस मीन के दूसरे साइड पे जाकर, this is called as one complete oscillation. But what are we seeing in this case? ये जो तीन फिगर्स ये दिखा रहे हैं कि A से छोड़ा B पे जाके रुका, so this is half an oscillation. ठीक है? So this is the story of half an oscillation. Now let us read on. Both points A and B are zero velocity points. साफ सी बात है, ए पॉइंट पे खींच के पकड़ रखा था, यहां से छोड़ा इसको, तो यहां पर भी वेलोसिटी जीरो थी। स्लाइड करता करता एनर्जी लूज करता करता बी पॉइंट तक गया और बी पॉइंट पे जाकर के फिर रुका। तो बी पॉइंट भी ऐसा पॉइंट है जहां वेलोसिटी जीरो है। सो एट बोथ द पॉइंट्स ए एंड बी देयर इज नो काइनेटिक एनर्जी फॉर द मास। इसी चीज को अपन टैकल करेंगे एंड वी आर गोइंग टू अप्लाई एनर्जी थ्योरम और कंजर्वेशन ऑफ एनर्जी। The system has pure potential energy and no kinetic energy at A and B locations. साफ बात हो गई। And once again, let me remind you, what is the potential energy that we are talking about? देखो A point और B point यहाँ पर मैंने ऊपर नीचे तो बना रखे हैं, लेकिन ये अलग अलग फिगर है। ठीक है, जमीन तो हॉरिजॉन्टल है, तो B पॉइंट यहाँ होगा। अगर इस फिगर में मैं B बनाऊं तो मास यहाँ पर दिखेगा आपको। So you see, in both the locations A and B, the mass is not changing height. And as long as mass is not changing its height above the datum level, it is simply running on a horizontal field. The potential energy due to gravitational remains the same. तो इसका मतलब A पॉइंट पे जितना पोटेंशियल एनर्जी ग्रेविटेशनल था, उतना ही पोटेंशियल एनर्जी ग्रेविटेशनल B पॉइंट पर भी है। तो कौन सी पोटेंशियल एनर्जी की बात हो रही है? हमने ये कहा कि ए पॉइंट और बी पॉइंट पे काइनेटिक एनर्जी तो जीरो है, बिकॉज दे आर जीरो वेलोसिटी पॉइंट्स। फिर ये कह दिया कि पोटेंशियल एनर्जी ग्रेविटेशन भी जीरो है, तो कौन सी एनर्जी हुई? ऑब्वियसली वी आर टॉकिंग अबाउट द स्ट्रेन एनर्जी ऑफ द स्प्रिंग, और in simple terms we are simply speaking about the potential energy of the spring, which we commonly refer to as PES। ठीक है, और पोटेंशियल एनर्जी ऑफ स्प्रिंग का जो जनरल एक्सप्रेशन होता है दैट इज हाफ ऑफ के into x square, where x is the stretch or compression. See, since x is being squared here, so potential energy of a spring can never be negative. It is always positive. चाहे आप स्प्रिंग को खींच के एनर्जी स्टोर करो, चाहे स्प्रिंग को दबा के स्टोर करो, पोटेंशियल एनर्जी ऑफ स्प्रिंग हमेशा कांस्टेंट, जो कांस्टेंट आएगी वो हमेशा पॉजिटिव आएगी। सो राइट हैंड साइड पे जब खींच के पकड़ा था तो पोटेंशियल एनर्जी ऑफ स्प्रिंग कितनी थी? हाफ ऑफ के एक्स ए स्क्वायर। लेफ्ट हैंड साइड पे जब मास जाकर के रुका तो आपने देखा कि मीन पोजीशन से स्प्रिंग कितना दबा? एक्स बी से दबा। तो अब इसकी पोटेंशियल एनर्जी कितनी है? हाफ ऑफ के एक्स बी का स्क्वायर। ठीक है, सो वी आर कंसिडरिंग द इनिशियल पोटेंशियल एनर्जी एट द स्टार्ट ऑफ द हाफ साइकिल and the final potential energy at the end of the half cycle, and these two are not same because xb is less than xa। तो इसका मतलब है स्टार्टिंग पोजीशन और एंडिंग पोजीशन पे जो पोटेंशियल एनर्जी का जो डिफरेंस आएगा ये कहाँ गया? दिस मस्ट बी इक्वल टू द एनर्जी लॉस्ट ड्यू टू फ्रिक्शन बिटवीन द सरफेसेस। एंड हाउ डू वी फाइंड द फ्रिक्शन? फ्रिक्शन पता करने का सिंपल कॉन्सेप्ट होता है, या सॉरी फ्रिक्शन के कारण एनर्जी लॉस कितना हुआ ये पता करने का सीधा सीधा कॉन्सेप्ट होता है कि भाई आप एक जमीन पे एक ऑब्जेक्ट को खींचते हुए ले जा रहे हो और फोर्स ऑफ फ्रिक्शन कंटिन्यूअसली कॉन्स्टेंटली पीछे को लग रहा है, तो ऑब्वियस सी बात है जहां इन दोनों के बीच में रगड़ होगी तो हीट एनर्जी में कन्वर्ट होती रहेगी आपकी एनर्जी। तो आपने कहा कि मैं इस बॉक्स को कितना खींच के ले गया? मैं इसको एक्स डिस्टेंस तक खींच के ले गया। सो अ फोर्स acting in the backward direction was forced to move by a distance of x, and energy, if not anything, is always equal to f multiplied by displacement. In this case, since f is negative, so the entire energy will be a negative energy, or rather it's a loss of energy। तो लॉस ऑफ एनर्जी कहोगे तो ये माइनस साइन लगाने की जरूरत नहीं है, आप सिर्फ ये कहोगे कि f इंटू एक्स का मैग्नीट्यूड ऑफ एनर्जी लॉस हो गया हमारा। So this is what we are going to say here कि मैंने अपनी पोटेंशियल एनर्जी इनिशियल लोकेशन पे नापी फाइनल लोकेशन पे नापी, दोनों सेम नहीं थी, तो गई कहाँ बाकी की एनर्जी? कितना डिस्टेंस ट्रेवल किया आपका मास? यहां से स्टार्ट किया और यहां पे रेस्ट पे आया, सो द टोटल डिस्टेंस ट्रेवल्ड इज दिस, and this is definitely equal to xa plus xb. So you say that energy lost in friction is F into xa plus xb. So now you can equate these two. इन दोनों को इक्वेट कर सकते हैं कि इनिशियल पोटेंशियल एनर्जी में से फाइनल पोटेंशियल एनर्जी माइनस करें तो इस एनर्जी लॉस के बराबर ही एनर्जी का लॉस हुआ है, और कहाँ गई एनर्जी? बस यही है, एक फ्रिक्शन ही है, एक दुश्मन हमारा जो कि एनर्जी खा रहा है. So using this equation, what I do is I take half k common in both of these expressions, और इसमें रह गया xa square minus xb square. इसका एक्सपेंशन होता है xa plus xb into xa minus xb. फिर xa plus xb जो है वो दोनों साइड में इक्वल टू के दोनों साइड में कैंसिल हो गई, and eventually I am left with this thing. So what I say is xa minus xb is equal to 2f by k. इसको बॉक्स कर रखा है, दैट मीन्स यू हैव टू रिमेंबर इट. दिस इज एन इम्पॉर्टेंट थिंग. और अपन ये पूरी कहानी क्या कर रहे थे? वी वर ट्राइंग टू डिस्कस रेट ऑफ डीके ऑफ ऑसिलेशंस. डीके ऑफ ऑसिलेशंस का मतलब ऑसिलेशंस का घटना. ये अपन ऑलरेडी देख चुके हैं कि डैम्पिंग के केस में आपका एम्पलीट्यूड यहाँ पहले इतना था, फिर इतना रह गया, फिर छोटा हो गया. सो इट इज कंटिन्यूअसली डिक्रीजिंग विद एवरी साइकिल. सो दिस इज व्हाट वी आर इंटरेस्टेड टू फाइंड. ये जो रिडक्शन हुआ है एम्पलीट्यूड का, ये है डीके, या फिर इसको और सिंपल टर्म्स में कहना चाहो तो रिडक्शन कह लो. ठीक है. सो वी आर इंटरेस्टेड टू फाइंड आउट हाउ मच इज द रिडक्शन इन एम्पलीट्यूड आफ्टर एवरी साइकिल. तो अपन ने ये डेरिवेशन हाफ साइकिल के लिए किया और ये पता किया कि एक्स ए मेरा इनिशियल एम्पलीट्यूड था, और हाफ साइकिल खत्म हुआ तो एक्स बी मेरा एम्पलीट्यूड था. तो एक्स ए माइनस एक्स बी जो है वो 2f बाई के बराबर आती है. ठीक है. Now, this same analysis can be repeated for the remaining half cycle. Remaining half cycle का मतलब है अब x b पे आकर के रुका है, अब आपको कुछ करने की जरूरत नहीं है, आप सिर्फ देखते रहो. देखते देखते क्या होगा, अब ये स्प्रिंग दब गई है तो अब ये उल्टा चलना स्टार्ट होगी. अब in the next half cycle this mass will start traveling towards the right, and once again when it reaches the mean position it won't be able to stop because of the inertia of its own mass, and it will overshoot the position and it will go somewhere to the right and then again stop. यहाँ पर जाकर के फिर स्टॉप हो जाएगी. अब ये पॉइंट सी हो गया, यू नेम इट एज पॉइंट सी, और इसकी जो डिस्टेंस है इसको एक्स सी मार्क कर लो, और उसके बाद आप अब ये वापस से एनर्जी थ्योरम लगाओ. अब आपकी इनिशियल पोजीशन बी थी और फाइनल पोजीशन सी है, एंड ऑब्वियसली एक्स सी इज लेस देन एक्स बी नाउ. सो यू विल इवेंचुअली फाइंड कि अब ये जो सेकेंड हाफ ऑफ साइकिल है उसमें एक्स बी माइनस एक्स सी भी 2f बाई के ही आएगा. सो द नेक्स्ट हाफ साइकिल ऑल्सो लूजेस द सेम अमाउंट ऑफ एम्पलीट्यूड. सो नाउ वी हैव समथिंग टू शो फॉर इट. अपन ने कहा कि फर्स्ट हाफ साइकिल में 2f बाई के, सेकेंड हाफ साइकिल में भी 2f बाई के, तो टोटल कितना हो गया 4f बाई के. दिस इज यू हैव समथिंग दैट यू हैव टू रिमेंबर फॉर योर एग्जामिनेशन. इसको रटना है. कांस्टेंट रेट ऑफ डिक्रीज पर साइकिल इन कूलम्ब डैम्पिंग. यानी कूलम्ब डैम्पिंग है तो हर साइकिल में पिछले एम्पलीट्यूड की जितनी वैल्यू थी मीटर्स में उसमें से 4f बाई के को माइनस कर लो तो पता लग जाएगा कि अगले साइकिल की शुरुआत में कितना एम्पलीट्यूड बचा है. और एक और साइकिल हो जाएगा तो बचे हुए एम्पलीट्यूड में से फिर 4f बाई के माइनस करो, and you keep on deducting the same constant value of 4f by k after every cycle to find out what is going to be the starting amplitude for the upcoming cycle. So this is how we get it. तो चूंकि 4f by k 4f by k जैसा इस फिगर में दिख रहा है, देखो यहां से स्टार्ट किया, दूसरा साइकिल यहां पर स्टार्ट हो रहा है, तो ऑब्वियस सी बात है कि अगर मैं ये वर्टिकल डिस्टेंस नापूं तो 4f by k आएगा, क्योंकि 4f by k से मेरा एम्पलीट्यूड रिड्यूस हो गया. This is the third cycle. Again, if I measure the distance between the previous cycle and this current cycle, again I will get 4f by k. This is what we have derived here. और ये देखो ये बात अपन डिस्कस कर चुके हैं already. This distance represented by the horizontal distance between two crests is the time period, which is 2 pi by omega n, and since omega n is equal to under root of k by n, this is the expression for time period. और अब इस केस में when you connect the peaks of all the consecutive crests, you will be obtaining a straight line. ठीक है? So this is a very crucial piece of difference between Coulomb damping and viscous damping. Viscous damping के केस में डिक्रीज ऑफ एम्पलीट्यूड तो मिलता ही है, but this is, if you connect the dots like this, you get a exponential curve. And in the case of Coulomb damping, decrease of amplitude will still be seen, but in this case when you connect the peaks of these, you get a straight line. So it's a linear decay. तो decay तो दोनों केस में है. You have a linear decay of amplitudes in the case of Coulomb damping, and you have an exponential decay curve or an exponentially decaying amplitude case in the case of viscous damping. This is a crucial piece of difference between the two types of damping. ठीक है, ऐसा क्यों होता है, लीनियर क्यों है, क्योंकि ये कांस्टेंट वैल्यू हर एम्पलीट्यूड से माइनस हो रही है, तो इसीलिए ये लीनियर एक लाइन ही बनेगी, सीधी सी बात है. यहाँ पर लॉगरिथमिक डिक्रीमेंट आता है. दिस वी हैव ऑलरेडी सीन इन विस्कस डैम्पिंग. एनीवे, so this is the end of our discussion for Coulomb damping. और Coulomb damping में फाइनल क्या लर्निंग पॉइंट्स हैं आपके. सारे डेरिवेशन वगैरह तो आपको याद करना ही है, यू हैव टू रिमेंबर ऑल द डेरिवेशन. देयर आर टू मेजर टेक अवे पॉइंट्स. टेक अवे पॉइंट्स का मतलब है कूलम डैम्पिंग हमने पढ़ ली, और अब कूलम डैम्पिंग से रिलेशन में हमें क्या चीज याद रखनी है एग्जाम के लिए, डायरेक्ट फॉर्मूला क्या याद रखना है. द थिंग दैट यू हैव टू रिमेंबर इज, फर्स्ट, the damped frequency or omega d happens to be the same as the undamped natural frequency equal to under root of k by m. The second point that we have to remember is that we have a linear decay of amplitudes for Coulomb damping, and 4f by k. F is the constant frictional force, k is the spring constant. 4f by k is the constant value by which amplitude reduces after every cycle. हर साइकिल के बाद 4f by k से एम्पलीट्यूड रिड्यूस हो जाता है. These are the टेक अवे पॉइंट. यानी कि कूलम डैम्पिंग से रिलेटेड ये तो 3 पॉइंट एक तरह से याद रख लो. सेकंड तो हो गया डीके ऑफ एम्पलीट्यूड इज लीनियर, और थर्ड पॉइंट हो गया कि कांस्टेंट वैल्यू से एम्पलीट्यूड हर साइकिल के बाद रिड्यूस होता है, और वो कांस्टेंट वैल्यू जो है जितने से एम्पलीट्यूड की कमी आती है वो 4f by k के फॉर्मूले से निकाला जा सकता है. फॉर एग्जाम्पल, अगर कोई कहे कि मेरा कूलम डैम्प्ड सिस्टम है, मैंने अपने मास को 1 मीटर खींचा था, अब एक साइकिल के बाद मेरा एम्पलीट्यूड कितना बचेगा, तो ये निकालने के लिए आप इनिशियल एम्पलीट्यूड 1 है उसमें से 4f by k को माइनस कर दीजिए, तो आपको ये जो क्वांटिटी मिलेगी ये मिलेगी मीटर्स में कितना एम्पलीट्यूड शेष रह गया सेकंड ऑसिलेशन की शुरुआत में, क्योंकि फर्स्ट ऑसिलेशन की शुरुआत में आपने 1 मीटर से खींच के छोड़ा था. So this is how you apply this value of 4f by k. ठीक है, so this is the end of our discussion for Coulomb damping. Now let us quickly do a numerical. This is illustrative example number 3.6.1 फ्रॉम द टेक्स्ट बुक ऑफ जीके ग्रोवर। जीके ग्रोवर के टेक्स्ट बुक में से लिया गया है ये। एंड इफ यू possess द बुक फिजिकली इट शुड बी ऑन पेज नंबर 85। पेज 85 पे मिलना चाहिए। Otherwise, for those who do not have the book, you can read it from here. A horizontal spring mass system with Coulomb damping has a mass of 5 kg। ठीक है, अपन डेटा लेना स्टार्ट कर देते हैं। साथ साथ में चूंकि अपन को Coulomb damping का horizontal spring mass सब दे रखा है, we can directly construct the system like this। ये m है, ये k है, ये वैल्यूज चाहिए। So let us say horizontal surface पे रेस्ट करेगा, रब करेगा, there is friction also। Now mass is 5 kg। Okay, so the value of m is given as 5 kg। It is attached to a spring of stiffness 980 Newton per meter। So thankfully this is in SI units। So सीधे सीधे मैं 980 न्यूटन पर मीटर लिख लेता हूँ। अगर सेंटीमीटर या कोई दूसरा यूनिट दिखे तो you need to convert it into SI units, Newton per meter। चलो this is good। The coefficient of friction is 0.025। coefficient of friction generally अपन mu से represent करते हैं। So let us write this as 0.025। ठीक है। You should know if you have studied engineering mechanics कि coefficient of friction की कोई unit नहीं होती। It is a dimensionless constant। So it is simply 0.025। Now this is what you have to calculate। Find the frequency of free oscillations। फटाक से आंसर आ जाएगा इसका। भाई फ्रिक्शनल डैम्पिंग हो रही है तो आप एक्सपेक्ट करेंगे कि कुछ डैम्प्ड फ्रीक्वेंसी आएगी। बट already we know from our takeaway point number 1 that the damped frequency is going to be the same as undamped frequency because this is Coulomb damping। तो आप सीधे सीधे कह लो कि भैया Coulomb damping है तो हमारी जो damped frequency है वो नेचुरल फ्रीक्वेंसी के बराबर ही होगी और अंडर रूट के बाई एम होगी। के पता है, एम पता है, so you directly substitute 980 upon 5 का अंडर रूट। इसका आंसर आना चाहिए अप्रोक्सीमेटली 14 रेडियंस पर सेकेंड। दिस इज योर आंसर टू फर्स्ट पार्ट। सेकेंड पार्ट, the number of cycles corresponding to 50% reduction in amplitude if the initial amplitude is 5 centimeter। इसको अगर मैं थोड़ा सा हिंदी में सिंप्लीफाई करके समझाऊं तो क्या बोल रहा है कि कितने साइकिल बीत जाएंगे, कंप्लीट साइकिल्स, जब आपका इनिशियल एम्पलीट्यूड अगर 5 सेंटीमीटर था तो 50% एम्पलीट्यूड खत्म होने में कितने साइकिल लगेंगे। वापस से रिपीट कर रहा हूं। इनिशियली मैंने स्प्रिंग को और मास सिस्टम को 5 सेंटीमीटर से खींच के छोड़ा था। 50% इसका एम्पलीट्यूड बच जाए, इतना होने में कितने साइकिल ऑसिलेशंस खत्म हो चुके होंगे। अब देखो ये इट्स अ वेरी सिंपल क्वेश्चन, बिल्कुल बेसिक क्वेश्चन है, लेकिन अब यहां पर अपना ये वाला फॉर्मूला काम आता है। मेरे को ये पता है कि हर ऑसिलेशन के बाद सपोज मेरा स्टार्टिंग एम्पलीट्यूड एक्स नॉट था फर्स्ट ऑसिलेशन, सेकेंड ऑसिलेशन में साफ सी बात है मेरा एम्पलीट्यूड जो होगा एक्स नॉट माइनस 4f/k होगा। इतना कम हो जाता है हर ऑसिलेशन के बाद। थर्ड ऑसिलेशन जब स्टार्ट होगा तो मेरा एम्पलीट्यूड एक्स नॉट माइनस 4f/k माइनस 4f/k, एक और बार 4f/k कम हो जाएगा। और चौथे ऑसिलेशन में एक्स नॉट माइनस 4f/k माइनस 4f/k माइनस 4f/k। So in every cycle I will see 4f/k amount getting subtracted from my x naught। तो ऐसे करते 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 देखो फर्स्ट साइकिल, सेकेंड साइकिल, थर्ड साइकिल, फोर्थ साइकिल, ऐसे करते करते ये पूछ रहा है कि कितने साइकिल बीत जाएंगे जब ये जो क्वांटिटी अपने पास शेष बचेगी ये x0/2 बचेगी। दिस इज व्हाट दे आर आस्किंग। ठीक है, सो लेट अस अप्लाई अ लिटिल बिट ऑफ बेसिक मैथमेटिक्स। पहले ये देखूं कि मेरा x0/2 है कितना। ये बोलता है कि भाई 5 सेंटीमीटर था, इसको एसआई यूनिट्स में कन्वर्ट करना पड़ेगा। 5 सेंटीमीटर मीन्स 100 से डिवाइड कर देते हैं, 0.05 मीटर्स। ये तो आपका एक्स नॉट है, यानी कि स्टार्टिंग एम्पलीट्यूड। तो 50% रिडक्शन के बाद एक्स नॉट बाई टू बच जाएगा। तो बचा हुआ जो एम्पलीट्यूड है ये कितना हो गया, 0.05/2, दैट इज 0.025 मीटर्स। दिस इज माई एक्स नॉट बाई टू। तो मेरा रिडक्शन इन एम्पलीट्यूड कितना हुआ, ये हुआ एक्स नॉट माइनस एक्स नॉट बाई टू, दैट इज अगेन एक्स नॉट बाई टू, सो इट इज ऑल्सो इक्वल टू 0.025 मीटर्स। अभी रिडक्शन क्यों मैं पता कर रहा हूँ, क्योंकि मेरे को पता है कि एक साइकिल में, इन वन साइकिल द रिडक्शन कितना है, 4f/k, और मेरे को टोटल रिडक्शन 0.025 मीटर तक पहुंचना है। भाई इतना रिडक्शन हो गया तब जाके ही तो एक्स नॉट बाई टू बचा है। ठीक है, तो एक साइकिल में 4f/k का रिडक्शन होता है, टोटल रिडक्शन हुआ है 0.025 का। तो कितने साइकिल लगे, कैसे निकालेंगे, ये देखो, ये बेसिकली 4f/k क्या है, दिस इज रिडक्शन पर साइकिल, और ये क्या चीज है, 0.025, टोटल रिडक्शन। मेरे को साइकिल्स चाहिए, कितने साइकिल हैं, तो साफ सी बात है, टोटल रिडक्शन के साथ डिवीजन करा दीजिए रिडक्शन पर साइकिल का, तो आपको इवेंचुअली नंबर ऑफ साइकिल्स मिल जाएंगे जितने में ये काम हो रहा है। ठीक है, so what we have to do is we simply have to find it like this. So number of cycles is equal to total reduction कितना है, 0.025 मीटर्स, डिवाइडेड बाय रिडक्शन पर साइकिल कितना है, 4f/k। बस ये गणित लगानी है। एफ देखें क्या है, फोर्स ऑफ फ्रिक्शन है, ये निकालना पड़ेगा अपने को। एम इज मास विच इज मूविंग, नीचे को mg लगता है, ऊपर को नॉर्मल रिएक्शन लगेगा, बट these vertical forces are always balanced for horizontal motion, so r is equal to mg। the force of friction, अगर वेलोसिटी इधर को है तो फोर्स ऑफ फ्रिक्शन हमेशा पीछे को लगेगी, and this force of friction is equal to mu into r, and since r is equal to mg, our f can be found by mu into mg। ठीक है, देखिए म्यू क्या अपने को कितना दिया हुआ है, अच्छा इसी में देख लेते हैं। म्यू इज 0.025, so f is equal to mu is 0.025, mass is 5 kg multiplied by 5 kg mass multiplied by small g कितना होता है, 9.81 मीटर पर सेकेंड स्क्वायर। so we are taking all SI units multiplied by 9.81। ठीक है, ये कैलकुलेट अगर आप करके देखेंगे तो दिस शुड कम टू बी इक्वल टू, एफ इज इक्वल टू 1.225 न्यूटन, इतना आना चाहिए। अपन को क्या कैलकुलेशन करनी है, नंबर ऑफ साइकिल्स निकालने के लिए ये करना है। तो एफ तो मिल गया, के दे रखा है आपको, के की वैल्यू है 980 न्यूटन पर मीटर। नाउ 0.025 डिवाइडेड बाय 4f डिवाइडेड बाय के, 4 into F is 4 into 1.225 divided by 980. This is number of cycles. ये calculation आप करें, the number of cycles should come out approximately to be 5. There is one important caution that I will give you. यहाँ पर एक बार अपन चेक करें कि ये let me take up my calculator, you also check it. मैं तो इसका आंसर किताब से देख के बोल रहा हूँ, but let us see if it exactly comes out to be 5 or not. ठीक है, so I will do 0.025 multiplied by 980. ये 980 जो है आप डिवीजन के नीचे डिवीजन है तो ये 980 ऊपर जाके मल्टीप्लाई हो जाएगा, ये आप जानते हैं. So this is 24.5 divided by 4, then again divided by 1.225. So this comes out exactly equal to 5. But suppose you do a calculation like this and your answer, एक hypothetical scenario बता रहा हूँ ताकि आप तैयार रहें, ठीक है. अगर ये 4.8 आता सपोज, तो क्या करते हैं, इसको कभी भी इक्वल टू 5 मत करना. 4.8 साइकिल्स का मतलब एक डिफरेंट है यहाँ पे. 4.8 साइकिल का मतलब है 4 साइकिल तो कंप्लीट कर लिए, लेकिन पांचवें साइकिल का सिर्फ 80% ही कंप्लीट कर पाया. So since there is damping, there is friction, this is a real vivid possibility. So you should not round off the number of oscillations in the case of Coulomb damping. Coulomb damping के केस में जो number of oscillation अगर 4.8 आया है तो 4.8 oscillations ही लिखें. This is important. But anyway, in our case, the answer fortunately came to be exactly equal to a round number 5. So this is your answer to the second part of the question. Third part of the question is, how much time was taken to achieve this 50% reduction? भाई कितना टाइम लग गया? टाइम का मतलब अब now they are asking it in seconds. Now this is directly connected to the answer that you got in the second part. 5 साइकिल लगी, एक साइकिल में कितना टाइम लगता है? किसी भी तरह का ऑसिलेशन हो, डैम्प्ड हो अनडैम्प्ड हो, जो टाइम पीरियड है, अगर अनडैम्प्ड है तो टाइम पीरियड जो है वो 2 पाई अपॉन ओमेगा एन होता है. अगर डैम्प्ड है तो टाइम पीरियड इज इक्वल टू 2 पाई अपॉन ओमेगा डी होता है. तो अपने केस में डैम्प्ड तो है, लेकिन फॉर्चुनेटली अपना ओमेगा एन और ओमेगा डी सेम है क्योंकि कूलम डैम्पिंग है. और इसकी जो वैल्यू है दैट इज अंडर रूट ऑफ के बाय एम. तो अंडर रूट ऑफ के बाय एम से अपन ने इसकी ओमेगा एन तो निकाले रखी है. ओमेगा एन देखें कितना निकला था. इट वाज 14 रेडियंस पर सेकेंड. तो ये तो अपने पास ऑलरेडी है. दिस इज, और रादर दिस, बोथ ऑफ देम आर द सेम. इट इज 14 रेडियंस पर सेकेंड. तो आपका टाइम पीरियड कितना है? 2 पाई अपॉन 14. अब ये जो टी है, दिस इज टाइम टेकन फॉर वन साइकिल. टाइम पीरियड का मतलब ही यही होता है. In periodic motion or oscillatory motion, T is the time taken to complete one cycle. आपका 50% रिडक्शन होने में 5 साइकिल लगे. So your answer is simply 5 times the time period was the total time taken to achieve 50% reduction in amplitude. This is basically a calculation of 5 into 2 pi divided by 14. So this should come out to be approximately equal to 2.242 seconds. This is the answer. Okay, so although this was a lecture which was recorded without the presence of any student, I still hope that I was capable of explaining all the concepts in sufficient detail. And I hope that nobody would have any confusion. But if you have any confusion of any sort in how any step was implemented during the numerical or during the derivation parts, please feel free to contact your teacher.